Hello guys, welcome on Tesla Adventures. In this video today, we are going to start the magnetism. And we know that the magnetism has four subdivided topics, which is moving charge in magnetic field, and second one is sources of magnetic field, third one is earth magnetism, and fourth is magnetism in matter. So this is magnetism, and it is subdivided into these four topics. Now let us see that first of all we are going to discuss the moving charges in magnetic field. You can see, we know that we have already studied in electrostatic that a rest charge produces a electrostatic field around it like this, and a moving charge produces, this charge is moving, so it will produce electric field as well as the magnetic field. We cannot refer this electric field as electrostatic field because this charge is not static. So we can say that the moving charge produces electric field and magnetic field around it. So this type of electric field is created by moving charge. You can see that initially this charge should be at the center of this bigger sphere, and the field lines would be like that. This is a negative charge, and after some time it has shifted to this new position and the field lines becomes like that. So this is the field pattern of moving charge, and it also produces the magnetic field. You can see that if this charge, positive charge, is moving in this direction with some velocity v, so on the axis of the velocity you can see that on these 2 points which are lying on the velocity axis, magnetic field is 0, and magnetic field around this charge can be calculated easily, and the direction of magnetic field is calculated by Fleming's right hand rule. You can place your thumb parallel to the velocity and you can curl the fingers of the right hand to find out the direction of the magnetic field. So you can see that if this in this diagram, this cross is representing the direction of velocity, so you can you can use the right hand and you can place your thumb in the direction of this cross, and cross means inside the plane of this board. So you can place your thumb in pointing inside the plane of this screen, and you can curl the fingers. So while you will curl the fingers, you would observe that these curls would be clockwise directions, and these curls, these circles would represent the magnetic field around this moving charge. And if this charge is coming out of this plane of the screen, so you can put your thumb in such a way such that the thumb is pointing out of this plane, and if you will curl your fingers of the right hand in such a way, then you would see that they would be making a anti-clockwise circles. These anti-clockwise circles are called as magnetic field around this charge. So we know that a charge moving with a constant velocity produces both electric and magnetic field, this we know, and a charge moving with some acceleration produces electric field, magnetic field, and electromagnetic waves around it. So but in this chapter obviously we have to deal with the magnetic fields only. Now there are 4 situations. You can see that there is a charge which is kept near a current carrying wire. This charge is at rest. So first of all we have to discuss the electric force on the current carrying wire and the charge. So you can see that this charge is at rest, and we know, we have already studied that the charge which is at rest will not produce the magnetic field, and we know that there should be at least two different fields to produce the force, which means that there should be at least two different electric fields to produce electric force, and similarly there should be at least two different magnetic fields to produce magnetic force. But in this case, the current carrying wire, this wire, is producing the magnetic field because electrons are moving in this wire in the downward direction. But this charge is not producing any magnetic field. So there is only one field. So the magnetic force will not be produced on any one of them. So magnetic force would be zero on both of them. But electric force, what can we say about the electric force? Now let me tell you that electric force on both of them will also be zero, and this is due to the fact that the current carrying wire is electrically neutral because it has equal number of electrons and equal number of positive charge. So it is electrically neutral, and therefore we can say that it will not produce any electric field around it, although this Q will produce the electric field around it. But we know that at least two electric fields are required for electric force generation, so there would be no electric force acting between them. Now in this second case, you can see that if this charge is moving with some velocity v, then obviously this moving charge will produce magnetic field, as well as this wire will produce the magnetic field. So there are two magnetic fields, so we can say that there would be a non-zero magnetic force acting on both of them. Okay, so magnetic force will not be zero, but still electric force will be zero, and this is again due to the fact that current carrying wire is electrically neutral. Okay, now in the third case, we can say that there are two current carrying wires placed parallel to each other. So the magnetic force on both of them will not be zero because they both will be producing the magnetic fields, and the electric force on both of them will be zero because they both would not produce any electric field. And if in the fourth case, you can see that there are two charges which are same charge, positive charges, and are moving in the parallel direction with same velocity v. So obviously in this case also there would be some electric force also between them. It would not be zero because charges will produce two electric fields, and due to their interaction electric force would be generated, and both of them will produce some magnetic field, and due to the interaction of magnetic field, magnetic force would be produced, and magnetic force in this case would be zero. Okay, so this is very important basic of this magnetic field, that a moving charge in magnetic field will experience the magnetic force. Now let us see that what conclusions we have drawn. First is that any field force is generated due to the interaction of at least two fields which are generated by two different sources. So we already have studied that only single electric field cannot produce an electric force. There should be a minimum of two electric fields to produce the electric force, and similarly there should be a minimum of two magnetic fields to produce the magnetic force. Okay, because these forces are produced due to the interaction of the fields. And in the second conclusion, we can say that the magnetic force is also generated due to the interaction of at least two different magnetic fields generated by the two different sources, which we have already discussed. Now a static charge does not create any magnetic field around it, hence it will not experience any magnetic force. Obviously if a static charge is being placed in the magnetic field, then there is only one magnetic field in which it is placed, but it is not creating any magnetic field, so there would be no magnetic force acting on that charge. But a moving charge in magnetic field can experience a magnetic force acting on it, but not always. Obviously, a moving charge can experience the magnetic force acting on it because there are two magnetic fields created by it, by that external, by that charge, and the other field is external field. But this is not the case always, because in some cases I would be discussing in the further part of this video that in some cases a moving charge also does not experiences any magnetic force on it. Now a current carrying wire, in a current carrying wire, electrons are moving, hence they are creating some magnetic field around it. Hence we can say that current carrying wire creates a magnetic field around it. And a current carrying wire can apply the magnetic force on a moving charge, obviously. This we have discussed. Now let us discuss, which we have already studied in class 10th, the Fleming's left hand rule. Now according to this rule, we have already discussed this rule for calculating the force on a current carrying wire, but we are applying this rule to calculate the force acting on a moving charge in the magnetic field. So again, if we stretch the thumb and first two fingers of our left hand perpendicular to each other, mutually perpendicular, then thumb will represent the direction of force, and this first finger would represent the direction of magnetic field, and the second finger would represent the direction of velocity of positive charge, because we know that the positive charge moves in the same direction of current in the presence of electric or magnetic fields. Now this F is given by the formula Q V cross B, where V is the velocity vector and B is the magnetic field, external magnetic field in which that charge is moving. This is the formula for the magnetic force acting on a moving charge, positive charge, which is moving in magnetic field. If charge is negative, the force would be exactly in the opposite direction of this force. Okay, and you can see that F, V and B should be are mutually perpendicular if V and B are having the angle 90 degree, and obviously F we know is the vector which is the result of the cross product of these two vectors. So the direction of F would be in the perpendicular direction of V cross B, which means that F is perpendicular to both V and B. V and B may or may not be perpendicular, but when we apply the Fleming's left hand rule, then in this case the fingers are mutually perpendicular to each other. Now let us discuss a question for better conceptual understanding of the situation. So there is a mystery room which is having no gravity, and a charge is placed in this mystery room, and it was found that this charge was at rest forever, and we have to check the presence of electric or magnetic fields in the room. So what could be the probable options which can be correct? So we know that first of all, if this charge is placed at rest and it remained at rest forever, then obviously it can be the case that both electric and magnetic fields are zero. Second case, in which electric field is non-zero and magnetic field is zero, cannot be the case, because if this charge is at rest always, then electric force should be always zero, because in the presence of electric field this charge would start to move, but it is obviously at rest forever, so electric field should not be there. So B is incorrect. Now C says that electric field is 0 and magnetic field is non-zero. This is correct option, because if electric field is 0, then this charge will not move, and if this charge will not move, then the magnetic force would not apply, magnetic field would not apply any force on the charge. So its presence or absence would not make a difference. And option D cannot be the answer, because if electric field is present, then this charge would start to move. So the correct answer of this question is A and C. Now in the same mystery room, if we projected a charge with some velocity and we observed that charge passed through the room undeviated, it does not change its direction in the complete motion. So obviously first option can be the case, because if there is no field, no electric, no magnetic field, then it would go undeviated. Second can also be the case if electric force is in the direction of the velocity of the charge. If V is like that and E is like that, then this charge will go accelerated, but it would not deviate. So second can also be the option. C option can also be the correct option, because if E is zero and B is non-zero, and if magnetic field is parallel to the velocity, then their cross product would be 0, so there would be no force acting on the charge. And D option, that electric field is non-zero, and magnetic field is also non-zero. This can also be the case, as if we can imagine that velocity, electric field and magnetic field are all in the same direction, then this charge will not experience any magnetic force, but it would experience an electric force, and it would be accelerated, but it would not be deviated, because acceleration and velocity are in same direction. So D can also be the case. And in the third part, we projected this charge, and this charge passed through the room unaccelerated. So this charge did not accelerate in the room. So we can say that A option could be the case, because if there is no field, then there would be no force acting on the charge and it would not accelerate. B option could not be the case, because if there is presence of electric field only, then this charge would experience a electric force, and therefore its acceleration would not be 0. C option can be the case, because if electric field is 0 but magnetic field is along the direction of velocity, then magnetic force would also be 0, so the charge would pass through the room unaccelerated. And D option could also be the case, that if magnetic and electric fields are in such a way such that the electric force acting on the charge is equal and in the opposite direction. Let us suppose that electric force is acting in this direction, F electric, and magnetic force is acting in the downward direction, and F electric is equal to F magnetic, then net force acting on the charge would be 0, and this charge would pass through the room unaccelerated. So the correct answer could be A, C and D. So this was the complete basics of the moving charge and magnetic field. In the next videos, I would be bringing some amazing concepts. Keep watching Tesla Adventures. Thank you.